Okay, let's dive into this. Welcome to today's Explainer. We're taking a fascinating journey through the mathematical universe right now. And, we're going to see how some of the most profound, abstract mathematical concepts actually begin with just simple, everyday physical actions. We'll start out with the perfect, fixed stillness of circles and eventually evolve all the way to the mathematics of pure motion. It's going to be a fun ride.
So here's our roadmap for today. We're going to hit 1. Defining the perfect circle. 2. Moving the circle's center. 3. The geometry of lines. 4. Calculating the slope. And finally, 5. The gateway to calculus.
All right, Section 1, defining the perfect circle. I want you to visualize that classic trick where you tie a pencil to a center point with a piece of string and just pull it taut and draw. Mathematically, a circle is exactly that. It's simply all the points at a fixed distance, which we call the radius, from a fixed central point. That's it. Every complex thing about circles builds entirely from this one elegant physical rule.
Now, imagine dropping that circle onto a coordinate graph, right at the origin, coordinate 0. If we want to find the distance of any point on that circle back to its center, we just use the classic Pythagorean theorem. The horizontal distance squared plus the vertical distance squared equals the straight line distance squared. And that naturally turns into this beautifully simple algebraic equation. X squared plus y squared equals the radius squared.
But here's the thing. The universe isn't totally static, right? And shapes definitely aren't permanently glued to the origin. Which brings up a really crucial question. What exactly happens to our perfectly simple mathematical formula when we pick this shape up and slide it somewhere else on the coordinate plane?
That brings us to Section 2, moving the circle center.
When we shift our center around, we basically just tweak our foundational formula to account for the new coordinates, introducing h and k to get our standard equation. Now, what's really interesting about this is how counterintuitive the math can look at first glance when dealing with negative coordinates. Because the formula is built on finding the difference between points, a negative coordinate literally flips the subtraction into a plus sign. So, if you see an equation with, say, an x plus 4 in parentheses, it actually means the center is pushed left to -4.
Sometimes a circle's standard equation gets expanded out into this long, messy polynomial. To clean it up, we use a technique called completing the square. Now, I know that sounds scary and brings up a lot of math anxiety, but it's really just a simple 3-step cleanup job. You move the constant over, separate your x and y variables, and then add the squared halves of your coefficients to both sides. Do that, and the equation neatly collapses right back into our standard formula, clearly revealing the center and the radius again. Easy.
And honestly, playing with this algebra yields some incredible surprises. For instance, imagine a geometric problem where you have to find all the possible points on a plane that are exactly 3 times farther from point A than they are from point B. Conceptually, that sounds like it would map out some irregular, wobbly egg-like shape, right? But if you plug that physical rule into our distance formulas and go through the steps of completing the square, boom, no way. It algebraically resolves into a brand new, perfectly round circle. It's an absolutely stunning example of how basic distance formulas turn geometric concepts into pure algebra.
Moving on to Section 3, the geometry of lines.
Let's shift away from fixed distances for a moment and focus on movement and direction. The absolute most important concept here is slope. Think of a playground slide. In math, slope simply measures exactly how much a line goes upwards or downwards for every step we take to the right. So if you have a perfectly flat, horizontal line, it doesn't rise at all, right? So its slope is exactly 0. Simple enough. But conversely, a vertical line pointing straight up never runs to the right. Mathematically, the tangent actually doesn't exist there, making its slope entirely undefined. Literally no slope at all.
And this brilliantly illustrates the whole point. There is a strict, undeniable connection between the algebra and the physical direction. A rising line has a positive slope, a falling line has a negative slope, flat is 0, vertical is undefined. The algebra perfectly dictates the physical reality of the line.
Section 4, calculating the slope.
So how do we find the actual number? Well, we use the slope formula. We represent slope with the letter m, and it's simply a matter of dividing our vertical change, which we call the rise, by our horizontal change, the run. It's just a ratio comparing how far up against how far over. Let's apply this to a concrete example from our source material. Let's say we have point P at coordinates 3, 4, and point Q at 5, -1. To
To find the rise, we subtract the y-coordinates. -1 minus 4 gives us a drop of -5. Okay, to find the run, we subtract the x-coordinates. 5 minus 3 gives us a run of 2. Rise over run, -5 divided by 2, or, written properly as a fraction, -2/5. And because it's negative, we know instantly, without even graphing it, that this line is falling as we move to the right.
And finally, Section 5, the gateway to calculus. Let's move to and see how this builds into the broader universe. Let's pull back the curtain for the grand finale here. Look at the distance formula we used for our circle and the slope formula we just used for our line. Notice anything? They are built from the exact same mathematical DNA, delta x and delta y.
So, the crucial point is summarized beautifully by this profound realization. Coordinate geometry is really teaching us how to understand change. We aren't just drawing static pictures here. The whole time, we've been secretly learning the foundational language of how things transform, move, and react. We are literally calculating change itself.
And you know, this sets up a spectacular evolutionary timeline. We start with the super simple geometric idea, rise over run. That gives us our algebraic slope. But once we understand slope, we realize we're actually measuring a rate of change. And once you are measuring rates of change point by point along a curve, well, you have just unlocked the ultimate tool of advanced mathematics, the derivative.
Which leaves us with the central, most provocative question of all calculus. How fast is y changing when x changes? The circles and straight lines we looked at today are just the training ground. Once you master this simple question, you can measure the curve of a rocket's trajectory, the flow of heat, or literally the curvature of space itself. So I want you to keep that question in mind, and let it guide you into your next mathematical adventure. Thanks so much for exploring the math universe with us today.